Today we're going to talk about something called conjugate acids and conjugate bases. And conjugate acid and conjugate bases come from our Bronsted-Lowry definition of an acid and a base. Okay, so can someone remind me what a Bronsted acid would be? Michael, what do you think?
Molecule that's a proton donor.
Bronsted acids and Bronsted bases deal with the transfer of protons. Okay, so a Bronsted acid would be something that's willing to donate a proton or to give up that H plus ion. Okay, that's a proton donor, and that's a Bronsted-Lowry acid. Okay, so we're going to talk about conjugate acids and conjugate bases in terms of that Bronsted-Lowry theory. Okay, so right now in your mind you need to be thinking about proton donators and proton acceptors. Okay, things that transfer that H plus ion. Okay, so a conjugate acid is a compound that forms, okay, so it's a new compound. It's going to be on the right side of your reaction if we're looking just at one-way reactions. This forms when a base, a Bronsted-Lowry base, gains a proton. Okay, so when a base gains a proton, it now essentially has one to give up, which kind of makes it like an acid, okay, which is why we call it a conjugate acid. Okay, so a conjugate acid is something that happens secondary. Okay, when that base gains a proton, it will become, or it will form what we consider a conjugate acid. Okay, so what do you think a conjugate base might be? If a conjugate acid is something that forms from a base gaining a proton, what do you think a conjugate base might be? Yeah, okay, a conjugate base is a compound that forms when a Bronsted-Lowry acid loses its proton. Then it becomes kind of a base substance. Okay, so these two things kind of happen in pairs and happen simultaneously. Oh, sorry, do you have everything you need? Okay, so let's go ahead and look at a chemical reaction, and we'll talk about the acid and base and conjugate base pairs. Okay, so go ahead and just get this chemical reaction written down and kind of get your head wrapped around what's happening, and then we'll talk about these pairs. This compound right here, this NH3 compound, is called ammonia. Okay, ammonia. It's reacting with water to form this compound right here. What's NH4 plus called? Ammonium. Good, that's one of your polyatomic ions. Ammonium, and it forms this compound which is called? Hydroxide. Good. OH minus is called hydroxide. So this is an acid-base reaction. Okay, this is an acid-base reaction. We have a base here in ammonia reacting with water, which in this case is acting as an acid. As we complete this reaction, we're going to form ammonium and hydroxide. Okay? Between these two, it's already pointed out clearly to us which is the base and which is the acid. This reaction, since we only have a single-headed arrow, is telling us it only is going to go to the right. Okay? What's it mean when we see a double-headed arrow? It can go back and forth. So in this case, we only have a one-way reaction. It's only going to go this way and then it's going to stop. So here, when NH3 gains this proton, we end up with NH4 plus. Okay? Now this compound right here, this ammonium compound, has a hydrogen that it's willing to give up to go back to ammonia. Okay? That's what it means when we say a conjugate acid. It's an acid because it has an extra proton that it's willing to give away, but it's conjugate because it comes from something else. Okay? And then if we look at water here, what's it doing from here to here? It lost a proton, right? It was an acid, so it gave up a proton. On the other side, it's down one proton, so it wants to take one. It wants to accept a proton, which makes it a base, a Bronsted-Lowry base. Okay? Does that make sense? Okay. So when we talk about acid and base reactions, we talk about them most of the time being in an equilibrium system. Okay? Equilibrium systems mean that reactions can go both forward and backward. Okay? Until they reach some sort of equilibrium, some sort of concentration equilibrium, and those are specific for each reaction. Okay, but most of the time these equilibrium reactions can go forward and backward. So once we see a conjugate acid and a conjugate base form, those two might combine again, donate that proton or switch that proton back so you get back to your original reactants. Okay, so when we say equilibrium, we see that double-headed arrow, and we know that the reaction can go both forwards and backwards. Okay, now we're going to look at the formation or the identification of a conjugate acid and base pair. Okay, a conjugate acid and base pair are essentially these black lines here indicate the pair. Okay, so an acid is paired with its conjugate base, and a base is paired with its conjugate acid. Okay, so when you're asked to identify a conjugate acid and base pair, you look for the same kind of root compound, except plus or minus a proton pretty much. Okay, so here we have our base, and it's paired with its conjugate acid. That would be considered the other half of its pair. Okay, so a base is paired with a conjugate acid, and acid is paired with a conjugate base. Are we clear with that? Yeah, Michael, what do you think?
So they'll pretty much have the same elements?
Yeah, most of the time you'll look for those same base elements, except plus or minus a proton, pretty much. Okay, and that's for pretty basic acid-base. What that carries true for most. Okay. Okay, now we're going to look at the strengths of conjugate acid and conjugate bases. If we have a strong acid, that means we have a pretty weak conjugate base. Tell me what is specific about a strong acid, or what's special about strong acids. I'm going to let someone else go. You can pick somebody if you want. Jack, tell me what's special about a strong acid. Good. Strong acids dissociate 100% of the time. Okay, every single molecule in a strong acid will donate its proton. Okay, so if we have a strong acid, we have a weak conjugate base. Okay, if an acid is a strong acid, the conjugate base is then less likely to accept a proton. Okay, because the acid gives up the proton so willingly, the base will be pretty unlikely to accept that proton. Okay, the same goes for the vice versa of that. If we have a strong base, that means we have a weak conjugate acid. Okay, so those are kind of the relative strengths and weaknesses of our conjugate acid and conjugate base system. If we have a strong base that dissociates readily, the conjugate acid that forms is less likely to give up the proton. Okay, so it's not going to want to dissociate very quickly or at all. Okay. If you look at page 485, it's going to give us a table of these strengths of acids and bases, and I want to talk about that table. All right, so go ahead and take a look at this table on page 485. If you look on the left side, we're looking at our conjugate acids, and we're looking on the right side, we would look at our conjugate base. Okay? On the left side of the table, the conjugate acids or the acids get stronger as you move up the table. Okay, so the top of the table are the strong acids. At the bottom of the table are very weak acids. Okay, ones that are unlikely to give up that proton. Okay, so on the left side we have strong acids at the top, weak acids at the bottom. If you flip to the right side of the table, that's all of our bases. We have very strong bases at the bottom of the table and very weak bases at the top. Okay, so this corresponds with our idea that a weak or a strong acid would mean a weak conjugate base. So if you look at the very first line of the table, it says hydroiodic acid. That formula is HI. Okay, if we look at the conjugate base that forms from that acid, that's our weakest base because it's at the top of the table. And bases get stronger as they go down the table. Okay, so here's the correlation here. If you have an acid that's at the top of the table, that means the acid is strong and the base is weak. If you have a base that's at the bottom of the table and an acid that's across from that, that'd be a weak acid but a strong base. Okay, so do we understand how to read that table? Okay. Okay, your homework assignment is page 489, number 1, A through C, and number 2A. And then on page 491, we'll do numbers 20, 24, and 28.